The next lesson is on estimating a population mean. We'll look at interpreting a confidence interval for a population mean, determining the sample size to obtain a level C confidence interval for a population mean with a specified margin of error. We'll describe how the margin of error of a confidence interval changes with the sample size and level of confidence C, and determine sample statistics from a confidence interval. In Section 8.1, we estimated a mystery mean by constructing a confidence interval using a sample mean 240.79. To calculate a 95% confidence interval for mu, we use a familiar formula: estimate plus or minus critical value times standard deviation of statistic. One sample z interval for a population mean, we choose a simple random size of n from a population having unknown mean mu and known standard deviation sigma. As long as the normal and independent conditions are met, a level C confidence interval for mu is x bar plus or minus c star times sigma over square root of n. The critical value z star is found from a standard normal distribution. The margin of error of the confidence interval for the population mean mu is z star times sigma over square root of n. We determine a sample size for a desired margin of error when estimating a mean in much the same way we did when estimating a proportion. Determine a sample size n that will yield a level C confidence interval for a population mean with a specified margin of error. Get a reasonable value for the standard deviation from an earlier or pilot study. Find the critical value z star from a standard normal curve for confidence level C. Set the expression for the margin of error to be less than or equal to ME and solve for n. Researchers would like to estimate the mean cholesterol level mu of a particular variety of monkey that is often used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter of the true value of mu at a 95% confidence level. A previous study involving this variety of monkeys suggests that the standard deviation of a cholesterol level is about 5 milligrams per deciliter. The critical value for 95% confidence is z star equals 1.96. We'll use sigma equals 5 as our best guess for the standard deviation. Multiply both sides by square root of n and divide both sides by 1. Square both sides. We'll round to 97 monkeys to ensure the margin of error is no more than 1 milligram per deciliter at 95% confidence. Administrators at your school want to estimate how much time students spend on homework on average during a typical week. They want to estimate at the 90% confidence level with a margin of error of at most 30 minutes. A pilot study indicated the standard deviation of time spent on homework per week is about 154 minutes. How many students need to be surveyed to estimate the mean number of minutes spent on homework per week with 90% confidence and a margin of error of at most 30 minutes? Here's the math. 90% confidence is 1.645 for z star. We take our sigma, which is 144 standard deviation, over the square root of n is less than or equal to 15. Do the math, move the n over, divide by the 15, square both sides, and we get about 286 students need to be surveyed in order to get a 90% confidence level. When the sampling distribution of x bar is close to normal, we can find probabilities involving x bar by standardizing. When we don't know sigma, we can estimate it by using the sample standard deviation, S of x. What happens when we standardize? This new statistic does not have a normal distribution. When sigma is unknown, when we standardize based on the sample standard deviation, our statistic has a new distribution called a t-distribution. It has a different shape than the standard normal curve. It is symmetrical with a single peak at 0. However, it is much more airy in the tails. Like any standardized statistic, t tells us how far x bar is from its mean mu in standard deviation units. However, there's a different t distribution for each sample size, specified by what's called its degrees of freedom. When we perform inference about a population mean using a t distribution, the appropriate degrees of freedom are found by subtracting 1 from the sample size, making df equal to n minus 1. We will write the t distribution with n minus 1 degrees of freedom as t with a subscript of n minus 1. Draw a simple random sample size n from a large population that has a normal distribution with mean mu and standard deviation sigma. The statistic t equals x bar minus mu over s of x over square root of n has the t distribution with degrees of freedom equal n minus 1. The statistic will have approximately a t to the n minus 1 distribution as long as the sampling distribution is close to normal. When comparing the density curves of the standard normal distribution and t distributions, several facts are apparent. T distributions have more area in the tails than the normal standard distributions. The density curves of the t distributions are similar in shape to the standard normal curve. The spread of the t distributions is a bit greater than that of the standard normal distribution. The t distributions have more probability in the tails and less in the center than does the normal distribution. As the degrees of freedom increase, the t density curve approaches the standard normal curve ever more closely. We can use table B in the back of the book or on your sheets to determine critical values t star for t distributions with different degrees of freedom. Suppose you want to construct a 95% confidence interval for mean mu of a normal population based on a simple random sample of size n equals 12. What critical t star should you use? In table B, we consult the row corresponding to degrees of freedom equals n minus 1, which equals 11. We move across to the entry that is directly above 95% confidence level. The desired critical t star is 2.201. Suppose you want to construct a 90% confidence interval for mean of a normal distribution based on a simple random sample of size 10. What critical t star should you use? Using the line df equals 10 minus 1, which equals 9, and the column with tail probability of 0.05, the desired critical value is t star equals 1.833. When the conditions for inference are satisfied, the sampling distribution for x bar has roughly a normal distribution. Because we don't know sigma, we estimate it by the sample standard deviation of s of x. The standard error of a sample mean is x bar, which is s of x over square root of n, where s of x is the sample standard deviation. It describes how far x bar will be from mu, on average, in repeated simple random samples of size n. To construct a confidence interval for mu, we place the standard deviation of x bar by its standard error in the formula for the one sample z interval for a population mean. Use critical values from the t distribution with n minus 1 degrees of freedom in place of the z critical values. That is, we take x bar plus or minus t star times s of x over square root of n. The one sample t interval for a population mean is similar in both reasoning and computational detail to the one sample z interval for a population proportion. As before, we have to verify 3 important conditions before we estimate a population mean. Is it random? Does the data come from a random sample of size n from the population of interest or a randomized experiment? Is it normal? The population has a normal distribution where sample size is large, n is greater than or equal to 30. Is it independent? The method for calculating the confidence interval assumes individual observations are independent. To keep the calculations reasonably accurate, When we sample without replacement, we should check the 10% condition. Verify the sample size is no more than 1/10 of the population size. The one sample t-interval for a population mean. Choose the simple random sample. A level C confidence interval is x bar plus or minus t star times s of x over square root of n, where t star is the critical value for t to the n minus 1 distribution. Use this interval only when the population distribution is normal or the sample size is large, and the population is at least 10 times as large as the sample. We want to estimate the true mean tension mu of all the video terminals produced this day at a 90% confidence level. If the conditions are met, we can use a one sample t-interval to estimate mu. We are told the data come from a random sample of 20 screens when the population of all screens produced that day. Since the sample size is small, we must check whether it's reasonable to assume the population distribution is normal. Examine the distribution of the sample data. These graphs give no reason to doubt the normality of the population. Because we are sampling without replacement, we must check the 10% condition. We must assume at least 200 video terminals were produced this day. Using our calculator, we find the mean and standard deviation of the 20 screens in the sample. Since n equals 20, we use t-distribution with d degrees of freedom, or df equals 19, to find the critical value. From table B, t star equals 1.729. Therefore, the 90% confidence interval is 306.32 plus or minus 1.729 times 36.21 over square root of 20, which gives us 292.32 and 320.32. We are 90% confident the interval from 292.32 to 320.32 captures the true mean tension in the entire batch of video terminals produced that day. Here's another example. The principal at a large high school claims the students spend at least 10 hours per week doing homework on average. To investigate the claim, an AP statistics class selected a random sample of 250 students from their school and asked them how long they spent doing homework during the last week. The sample mean was 10.2 hours, and the sample standard deviation was 4.2 hours. Construct and interpret a 95% confidence interval for the mean time spent doing homework in the last week for students at the school. Based on the interval, what can we conclude? Here's our results. We want to estimate mu, the mean time spent doing homework in the last week for students at the school with a 95% confidence. We will construct a one sample t-interval provided the following conditions are met. Is it random? The students were randomly selected. Is it normal? The sample size is large, n equals 250. Because we're sampling without replacement, we check the 10% condition. It is reasonable that there are more than 2,500 students at this large high school. There are 249 degrees of freedom. We want 95% confidence. We use the t-table. We'll use the degrees of freedom of 100 to get critical value of t star equals 1.984. We do the math and get an interval of 9.67 to 10.73. Since the interval of plausible values includes values less than 10, the interval does not provide convincing evidence to support the principal's claim that students spend at least 10 hours on homework per week on average. The stated confidence level of a one-sample t-interval for mu is exactly correct when the population distribution is exactly normal. No population of real data is exactly normal. The usefulness of the t-procedures in practice, therefore, depends on how strongly they are affected by lack of normality. An inference procedure is called robust if the probability calculations involved in the procedure remain fairly accurate when a condition for using the procedures is violated. Fortunately, the t-procedures are quite robust against non-normality of the population except when outliers or strong skewness are present. Large samples improve the accuracy of critical values from the t-distributions when the population is not normal. Except in the case of small samples, the condition that the data come from a random sample of randomized experiment is more important than the condition that the population distribution is normal. Here are practical guidelines for the normal condition when performing inference about a population mean. Sample size is less than 10. Use t-procedures if the data appear close to normal. If the data are clearly skewed or if outliers are present, do not use t. Sample size at least 15. The t-procedures can be used except in the presence of outliers or strong skewness. Large samples. The t-procedures can be used even for clearly skewed distributions when sample size is large, roughly n is greater than or equal to 30. Determine whether we can safely use a one sample t interval to estimate the population mean in each of the following settings. To estimate the average GPA of students at your school, you randomly select 50 students from your class. Here is a histogram of the results. Since the sample of 50 students was only from your class and not all students at your school, we should not use a t interval to generalize about the mean GPA for all students at the school. B. The dot plot below shows the amount of time it took to order and receive a regular coffee and 5 visits to a local coffee shop. Since the sample size is small and there is a possible outlier, we should not use a t interval. And our last one, C. The box plot shows the SAT math score for a random sample of students at your high school. Since the distribution is only moderately skewed and sample size is larger than 15, it is safe to use a t interval. Here's a summary of what we learned. In the next chapter, we'll learn how to test a claim about a population.